This video covers 3 recurrence relation examples. For each, we'll work out how to manipulate to get an informal guess that you can use for the substitution method, or that you can formalize for the recursion tree method, where those methods were covered in previous videos. Why 3 examples? Each example is similar, but slightly different, and after we've seen all 3, we will be ready to generalize them into a form used for the master theorem by the master method, our next method for solving recurrences. To understand our equation manipulations, you do need to know the geometric series. If you want to review it, like a good fairy godmother, your wish is my command. I have a video on it too. So, we have some recurrence relation. T of n equals 7t of n over 3 plus n squared. To get a guess for its order of growth, like in our recursion tree video, we plug into the t of n over 3 term using the recurrence relation itself, and then we'll distribute that 7 over both terms. We can plug in again and distribute again, and then maybe one more time. Here, I also notice that the n squared term can be taken out of all of the non-recurrence terms, and it looks like we have a general form for the equation that we could prove by induction if we wanted to. But we won't do that here. Instead, we'll just treat it as if we're trying to get a good guess for the substitution method, so we assume the general form is correct and try to figure out what order of growth it would imply if it was. In order to make that t of n over 3 to the I term disappear, I'm going to pick an I so that n over 3 to the I equals 1. That is, I equals log base 3 of n, and I plug in. That makes the recursion bottom out at t of 1, which I will, as usual, assume is bounded by a constant. Now, I personally have very little intuition of how 7 to the log base 3 of n grows, but it equals n to the log base 3 of 7, which grows like n to the 1 point something. So it looks like this entire equation grows like n to the 1 point something plus n squared times this summation. But what is this summation? Well, that's where our geometric series knowledge comes in. That is a decreasing geometric series, and it is proportional to the largest or first term in the series. So here it looks like t grows like n squared. If you want, you could either use n squared as a guess and prove that it really does work using the substitution method, or prove that the general format above holds, and then this would count as a recurrence tree proof. But we're just going to move on to the next examples. I won't do each of them from scratch because they look a lot like this example. So when I had worked out this general form guess, there wasn't anything particularly special about the 7 term. If that 7 changed into a 9, pretty much everything here would stay the same, except the 7's, of course. So how does that change our outcome? I still want the recursive t of n over 3 to the I term to bottom out, so I'm still going to plug in I equals log base 3 of n to make that happen. That math looks just like it did before, except for 2 changes. First up, the first term is now n to the log base 3 of 9, or n squared, instead of n to the 1 point something. Next, that summation is no longer a decreasing geometric series. Every term is exactly 1. So we just need to count how many terms there are, and there are log base 3 n terms. So in this case, we get a guess of n squared log base 3 of n, or just n squared log n for our growth. Again, we could then use that work as part of a substitution method or recurrence tree method proof. For our last example, we're again going to take a similar recurrence, but instead of a 7 or 9, we'll make that a 10. And once again, all of the math works out in a way very similar to before, again with two changes. Now, the first term is n to the log base 3 of 10, or n to the 2 point something. And because 10/9 is larger than 1, the series is now an increasing geometric series. Its summation is going to be proportional to the largest, or last term in the series, or 10 divided by 3 squared, all to the log base 3 of n minus 1. There's a bit more algebra for this one, but we work it out here, one step at a time, and the n squared terms kindly cancel. It gives a guess that the whole equation grows like n to the log base 3 of 10, or n to the 2 point something. So it turns out that a lot of divide and conquer algorithms end up giving recurrence relations that have analysis that looks very similar to one of these three cases. You work them out and end up with a decreasing or flat or increasing geometric series. The master theorem generalizes this approach so that for those recurrence relations, you don't have to work out any guess. You just need to do some quick analysis to ensure that you fall into one of the three cases, and then you apply the theorem, plug and chug, and it tells you the order of growth for the recurrence relation. The next video generalizes these three examples to try to justify a simple version of the master theorem. It also covers some cases where the master method doesn't work. But for now, I've got some glass slippers to deliver.